Ever get this feeling like reality is like way weirder than we think?
Yeah, definitely.
Today we're going deep on something that takes that weirdness to a whole other level, I think. We're talking about the many worlds interpretation of quantum mechanics.
Okay, so what's so fascinating about the many worlds interpretation is that it really starts with kind of a simple idea, right?
Yeah.
What if the universe doesn't just, allow for every possibility? What if it actually, like, realizes all of them all the time?
So we're talking about every quantum measurement, every coin flip that could have gone the other way actually does go the other way, just in a different universe.
Exactly.
Okay, so there's a me out there somewhere who made different choices. Okay, that's a lot.
Right. It's a lot to wrap your head around.
Yeah.
But for a moment, just imagine the implications here. The Schrodinger equation, the one that's kind of like the rule book for how quantum systems behave,
Right.
that would hold true everywhere. No need for this mysterious collapse of the wave function.
Okay, so no more collapsing wave functions, but then, and here's the big question that jumps out to me. If every outcome has its own universe, its own separate existence out there somewhere, where does that leave probability?
Yeah.
If I flip a coin, it lands on heads. There's another me out there staring at tails.
Right?
How can we even talk about the odds of something happening in a world where everything's already happened?
It's like you've hit on like the central paradox of the many worlds interpretation, right?
Mm.
It's like saying, okay, if every book imaginable, literally every book exists in this like vast cosmic library, okay, what are the chances of you picking up this specific book? The 100% right.
It's got to be in there somewhere.
It's got to be in there somewhere, but that doesn't really capture the whole picture, does it?
No, not really.
No.
And that's what's so interesting, because today we're looking at this paper, and it argues that to understand probability in the many worlds interpretation, we have to understand this idea called self-locating uncertainty.
Yeah, and you see, because a lot of attempts to reconcile this idea of probability with many worlds rely on this thing called branch counting. And the idea is pretty simple. More branches, higher probability.
Okay.
Right.
So my coin flip, 2 branches, 1 heads, 1 tails, 50-50 chance.
Right, exactly. But as this paper points out, and this is where it gets really interesting, there are some pretty significant problems with that approach.
Yeah.
And to understand why, we need to kind of back up and make sure we understand this other key concept that often gets overlooked in these discussions, which is decoherence.
Decoherence. Okay, this is where it starts getting really quantum, right?
It is. It is.
Uh-huh.
But it's also crucial to grasping how these many worlds actually emerge in the first place. So essentially, decoherence is the process by which quantum systems lose their, for lack of a better term, quantumness, right? They start behaving more like the classical objects that we're used to in our everyday experience.
So it's like those branching universes are somehow separating from each other?
That's a really good way to think about it, yeah. So let's say you have a quantum particle in a superposition of states. Think of it like our coin spinning in the air. It's both heads and tails at the same time.
Okay.
Decoherence is what happens when that particle interacts with its environment.
Mm-hmm.
So that could be the air molecules around it, the measuring device,
Oh, wow.
even stray photons, right? In a way that essentially records its state.
So it's not just the coin flip. We've got information about the flip kind of scattered all over the place now.
Yeah.
In the air, on the table, everywhere.
Exactly. And that information spreading out, that is the essence of decoherence. And it creates a situation where these different branches, these different outcomes, become so entangled with the surrounding environment that for all practical purposes, they're impossible to bring back together.
So even though, like, the math might say there's still this big interconnected wave function, these branches have become separate worlds in reality.
Precisely. And that sets the stage for, I think, the real puzzle of probability in many worlds. Because if we can't interact with those other branches, if they're essentially isolated realities, then why should we care about the probabilities at all?
Right.
And that's where this idea of self-locating uncertainty comes in.
Okay, so what is self-locating uncertainty, and how does it tie into all of this? Okay, so walk me through this.
Yeah.
How do we wrap our heads around self-locating uncertainty?
To understand this, let's imagine you're, a participant in this, like, very strange experiment.
Okay.
And this is where our friend Alice comes back into the picture. You might remember Alice from earlier discussions about quantum mechanics, right?
Right, always finding herself in these weird quantum conundrums. Poor Alice.
Exactly. She always seems to find herself in these perplexing situations. So in this scenario, Alice agrees to measure the spin of a particle, right?
Okay.
But here's the catch. depending on the outcome of her measurement, another measurement might happen, or it might not. And for, like, a crucial period of time, Alice is kept in the dark about,
Yeah.
about the results.
Oh, okay, so she doesn't know what's happening.
Exactly, she's in the dark.
Okay.
Now, you might be thinking, okay, that's a little weird, but what's the big deal, right?
Right.
But here's where the many worlds interpretation takes this to a whole other level. Because in many worlds, every possible outcome of those measurements is happening somewhere. Right?
Okay.
So there's now a version of Alice who saw one result, another version who saw a different result, and potentially even more Alices, depending on what those additional measurements entailed.
So we've got multiple Alices running around the multiverse,
Exactly.
and none of them know which one they are.
You got it. And that, my friend, is the essence of self-locating uncertainty.
Mm.
It's not that the universe itself is uncertain, right? Because after all, in this view, every possibility is playing out somewhere. The uncertainty lies in knowing which of those possibilities you, the observer, are, like, embedded in.
It's like, oh man, this is a lot. So it's not just the coin flip anymore. It's like, I'm losing track of which me is watching the coin flip.
It's like waking up in that giant library we talked about earlier,
Yes.
surrounded by infinite copies of yourself with no way to tell which copy you are.
Okay, yeah, that's a whole other level of existential dread. It's like, oh man, where am I? This is too much. Okay, but I see how this is working now. But I'm also starting to see where this whole branch counting thing starts to fall apart.
Exactly.
Because if you're Alice and you're in this situation and you start getting these little clues about what happened, maybe you overhear the researchers talking, you see a piece of equipment that gives you a hint, you start to realize, oh, maybe there are more Alices out there than I thought.
Right.
But the thing is, the spin that you observed, your experience hasn't changed. So that branch count, it can fluctuate based on information that's totally external to your reality.
It's true.
And that feels like a problem, right? Because now my sense of probability, my sense of how likely I am to be experiencing this thing, it's all dependent on these external factors that really have nothing to do with me.
100%. And that brings us to, like, the heart of the paper's argument, which is this idea of the Epistemic Separability Principle, or ESP.
Okay, ESP, that's a good one.
Catchy, right?
So this principle, it's basically saying, look, what happens in another branch stays in another branch.
Yeah.
My odds, my chances of experiencing this outcome shouldn't be swayed by, like, some random thing happening a billion light years away in some other reality.
You got it. Just like that library analogy, right?
Right.
Your chances of being a particular copy of yourself shouldn't be affected by, someone adding a new wing to the library a billion light years away.
Mm-hmm.
Your reality, your subjective experience should be independent of those kinds of changes.
Okay, yeah, that makes sense.
Right.
It feels right, even if, again, we're dealing with some pretty heavy stuff here.
Sure.
But so how does this ESP connect back to the Born rule? That equation that tells us how to actually calculate probabilities in quantum mechanics.
Well, and this is where things get, like, really interesting, because what the authors of this paper have done is shown that the epistemic separability principle, this seemingly, like, simple idea about the independence of our experiences, actually leads us directly to the Born rule.
Wait, really?
Yeah.
So just by saying what happens in Vegas stays in Vegas, but for the multiverse,
Right, exactly.
we get one of the most important equations in quantum mechanics.
Pretty much, yeah.
That seems like a huge leap.
It is a big leap, and I think it has some pretty profound implications for how we understand probability in this many worlds framework. Because what it's suggesting is that the Born rule isn't just, some arbitrary mathematical tool that physicists came up with. It's a direct consequence of how we as observers are embedded within this larger multiverse.
Okay, give me a second to process that.
Yeah, it's a lot.
So decoherence, making these separate worlds, self-locating uncertainty, making us question our place in all of it. And now this, ESP, tying it all back to the Born rule.
It all fits together.
It's a lot, but there's still one thing that we haven't really talked about, which is, okay, so what? If all of these outcomes are actually happening, why does any of this matter for our everyday lives? Like, why should I choose the salad over the donut if somewhere out there another me is, like, already enjoying both? It's like, I get to have my cake and eat it too, right?
It seems that way, doesn't it? But you have to remember, even though every version of you is out there somewhere in this crazy multiverse,
Yeah.
you only ever get to experience one of them.
Right.
And that's where this whole question of choice comes in, right? The significance of probability.
Okay.
So imagine you're about to, place a bet on a coin toss.
Let me guess, a quantum coin toss.
Of course.
With infinite me's.
Naturally.
Placing bets across the multiverse. Okay.
Exactly. So even though some versions of you will win and some versions of you will lose, right here, right now, in this moment,
Right.
you still have to make a choice.
Heads or tails.
Do you bet or do you walk away?
Right. Yeah, no, that makes sense.
Right.
Even if I can't, like, have a conversation with those other me's out there, the choice I make here determines what I experience, what I
That's right.
learn, how my little story unfolds.
100%. And what the authors of this paper argue is that in making those choices and navigating this, this branching reality,
Right.
it makes sense to kind of align our decisions with the probabilities that are dictated by the Born rule.
Okay.
Because even though every outcome is real, in some sense, they're not all equally likely from your perspective.
Right.
From the perspective of the you that's living out this particular branch of the wave function.
So it's like, even though according to many worlds, everything's already happened, right? It's deterministic.
Right.
Every possibility is out there.
Right.
From our limited point of view, it feels like probability is a thing.
It does.
And it makes sense to, like, act accordingly.
Exactly.
Okay, I like that. So that's a nice way to bring it back down to earth.
And it leads to, I think, another fascinating aspect of this paper, which is that it might actually give us new ways to think about testing the many worlds interpretation itself.
Okay.
Because if our choices and the outcomes that we experience are influenced by this born rule,
Right.
then we should be able to look for evidence of that and how our universe evolves, even if we can't, directly observe these other branches.
Oh, interesting. So instead of looking for parallel universes, we should be looking for the fingerprints of probability. But how is that affecting what's happening here?
It's like trying to understand the shape of a mold by looking at the patterns it leaves on the objects it touches.
Okay.
We may not be able to see the mold itself, but we can infer its presence and even some of its properties by carefully studying those imprints.
That's really cool. Okay, so this has been, I'm not going to lie, a pretty wild ride.
Yeah.
Many worlds, the nature of probability, the role of the observer.
It's a lot.
What's like the biggest thing that you're taking away from all of this?
I think for me, what's really sticking with me is this idea that even in a universe where literally every possibility is realized, where every quantum coin flip is spawning off countless new branches of reality, the question of what we experience, what we perceive as real, comes down to this fascinating interplay between our own subjective experience and these underlying mathematical laws that are governing this, this strange and wonderful multiverse that we find ourselves in.
Yeah, it makes those little everyday choices feel a bit more significant, right? Like,
Yeah.
what am I doing here? What's going on? So, to everyone listening out there, the next time you're faced with a choice, big or small, just remember there might be a version of you out there somewhere in the multiverse living with the consequences of the path you didn't take. But for you, the adventure continues right here in this branch of reality. And who knows what amazing discoveries await us as we keep exploring this wacky world of quantum mechanics. Thanks for joining us for this deep dive. We'll catch you next time.